Hi everyone. I want to go through 10 questions about finding vectors, either normal vectors or direction vectors, based on different types of inputs and the different formats that these questions can be asked in. So question 1, we're asked to find a vector that is parallel to the line given x of t is equal to 1, 3 plus t times 5, negative 6. So I'm going to do extra work for these questions by drawing some pictures. So the picture I want to draw for this question is I want to draw this line that's given. And every line contains lots of points. I'll label one of them, call it the point P. And we could use the point P that's given in the point normal form, the point parallel form of the line that the question gave us. So we could use that as a point vector for the point P. It goes from the origin to the coordinate 1, 3. Now, the other element of a line that we could use is the direction vector for the line. So that's given here as 5, negative 6. So I'll label that as well. That's direction vector v. And on the picture, there it is. And the direction vector, by definition, is parallel to the line. Now, because the direction vector for the line is given to us, all that we need to do in this question, to answer the question, is to state that v equals 5, negative 6 is parallel to the line. So no real work is needed except to know what this definition is. That's our answer. Okay, second one. We're given a similar question, find a vector that is parallel to the line 3x plus 5y is equal to 7, except here we don't have a line given in point parallel form. We have a line given in point normal form. Now, this form for a line is perfectly fine in 2D. We can't do it in 3D. In 3D, point normal form defines a plane, but in 2D, it defines a line. I'm going to, again, do extra work by drawing a picture. There's my line. And it has a point P, which we could find if we were desperate, if we needed to. We could find a x, y coordinate by choosing x and solving for y, or choosing y and solving for x. It also has a direction vector v. It's on the line. But neither piece of information is directly given. We can get the direction vector v, which we could then use to answer the question for finding a vector that's parallel to the line. It requires a little bit of work. I'm going to label one more thing on this picture that we could have labeled on the last one. Actually, I'm going to go up and add it there as well. It's an important thing to label sometimes. Okay. Let's call it the normal vector n. Just a vector that's perpendicular or 90 degrees to the line. And we can define that vector for the first example, for the first question, normal vector n. We get that using the flip trick. So we flip the direction vector to get the normal vector in 2D. So we take the direction vector v and flip them. So the negative 6 goes first, and the 5 goes second, and then we choose where to put an extra negative sign. So do we multiply the first component by -1 or the second component by -1? I'm going to multiply the second component by -1. So it was originally -6, so multiply by the -1, that's +6. If you take the dot product with n and v, you get 0, and that's one of our definitions for two vectors that are at 90 degrees or perpendicular or orthogonal to each other. Now, we didn't need that for the above question. The question was answered just by reciting the direction vector. But in this question, we have to do something similar. We're given the normal vector, n. Our n comes from the coefficients in front of x and y. So the first part of the normal vector is the coefficient in front of the x. Second part of the normal vector is the coefficient in front of the y. That's a 3, 5. And we want the direction vector. we've got to work backwards. And we get that by flipping. Flip V. No, flip, not flip V, flip N to get V. Works both ways. So our direction vector V, that is going to be parallel to the line. We switch the 5 and the 3, and then you decide you want to multiply the first component by -1, or the second component by -1. I'll multiply the second this time. It's up to you. You can put the first, -5 comma +3 is also a valid solution. Because that's our answer. That is parallel to the line. Okay, next one, number 3. Find a vector that is orthogonal to the line. Draw a line. Label some stuff on it. There's a point P on the line, has a direction vector V, and it has a normal vector N. Okay, this time the direction vector V is given to us. We have direction vector V that is 7, 8. Now, we want a vector that is orthogonal. That means we want a normal vector. So again, we're going to take our direction vector and flip. Get N by flipping V. So our normal vector N that is orthogonal to the line is going to be given by flip them, so there's an 8, 7, and I'm going to put a negative in front of the 8 this time. And if someone else says, I think the answer is 8, -7, then they're also right, because that's another vector that's orthogonal to the line. If you wanted to draw that vector, you could, if you want to draw them both answers in this schematic picture, you could put a vector that's pointing in the opposite direction to N, but still 90 degrees to the line, so going down and to the right. But all this is just, I mean, this picture doesn't, well, it does in this case, but I mean, these are just schematic images. They're not meant to actually represent the line. They're more meant to represent the components of the line in a more general sense. Okay, next one. Find a vector that is orthogonal to this line. And again, I'm going to draw the line. That has a point, at least one point P, has an infinite number of points, but there's one of them that has a direction vector V and has a vector N. Alright, and orthogonal means you want N. We want the normal vector for the line. Now what are we given? We're given the normal vector, the components, or the coefficients rather, in front of x and y. So we just have to state that N is equal to 5, -2. And we don't need to use the 3 at all. Just like in the previous examples, we didn't need to use the point. We just need the direction vectors here. We just need the coefficients in front of x and y. Now we could have been asked to find a vector that is parallel to this line. So direction vector V is equal to, we do that by flipping 2, 5. Components, multiply one by -1, so I multiplied the first by -1, so -1 times -2, +2, and that would serve as a direction vector. However, in this problem, we were not asked for that. We were asked just for the normal vector. We were asked for a vector that is orthogonal, not at 90 degrees to the line. Okay, number 5. Find a direction vector for a line that is orthogonal to this line. Here we go. There's our line that has a point P on it, has a direction vector V, and has a normal vector N. Now this time we're not given n. We want n. We're asked for, oh wait, I lied. Let's see, make sure I answered all those correctly. Yeah, orthogonal. Oh, this is a trick question. I didn't even read it right. So let's read this carefully together. My own question too. Find a direction vector for a line that is orthogonal to this line. So I'm going to draw two lines here. Here's the first line. This is the line x of t. And it has all types of stuff. It has a point P on it. I won't label the point P anymore. It's just going to cause some clutter. It has a normal vector n and has a direction vector v on the line. Now what are we given? We're given the direction vector v. V is 2, 3. For that line. However, we're looking for a direction vector for a line that is orthogonal to this line. So this is a line orthogonal to that line. We'll call that the new line. And it also has a normal vector and a direction vector. So here's the normal vector for the line. And here's a direction vector for the line. Now I can go back, jump back and label the first line components. N we get by flipping. So we get -3, +2. That's one potential normal vector that we could use. Now we're looking for the direction vector for the second line. We want a direction vector for the second line. We want the blue V here. Now look at the arrow. The arrow for the blue V lines up with the reddish brown N. So direction vector V is collinear to the normal vector for the given line, not the new one. So we can recycle, we can reuse it. So we can let V equal -3, 2. This is a trick question. There are two lines involved. There is the given line, x of t, and then it says for a line that is orthogonal to that line. So we want another line that's at 90 degrees to the original line, and we want that one's direction vector. You have to read these very, very carefully. I'm going to go back up and make sure I didn't screw any of these up. No, there's only one line involved in these. Yeah, they're not asking about relationship between two lines, so that's good. Okay, I'll do a bunch more of those because they're confusing. Find a normal vector for a line that is orthogonal to this given line. Okay, here we go again. I'm going to draw the first line, x of t, and then we have a new line, but let's label the components. We have the normal vector n, a direction vector v. This line has the direction vector v given as 6, 9. That means the normal vector n we can get by flipping as -9, +6. I'm going to draw the second line. That's our new line. It also has a normal vector n and a direction vector v. I'm really using v and n for both of them because I have colors. If you have pencil, get colors. No, if you demand that no colors be allowed except the gray of a pencil, or the blue of a pen, then don't use N for both. Use M for the second one. Actually, I'll do that here. I'll pretend I don't have colors. M, and instead of using V, I'll use U. So it has this second line has a direction vector M, or a normal vector M, and a direction vector U instead. Okay, now we want a normal vector. We want M. We want the normal vector for the new line. And look at what it lines up with. It lines up with being collinear, pointing in the same direction as V. Pointing the same way. Thus, our normal vector M is 6, 9. Don't try to do these without a picture. Think it out. Draw it out. Just reading the question, find normal vector for a line, that's what we're talking about to the line. If you don't draw it, you can be saying, well, do I flip them? Do I just use 6, 9? Do I use -9, 6? What am I supposed to do? And then you may make a weird tree diagram. I've seen these. I've seen study sheets with these things, these weird tree diagrams. We'll write different pathways. Like if it's this, if it's asking for a normal vector for a line that's orthogonal, and the line's given in point, like it's really demented. And you're going to waste all types of time studying in a garbage way. It's like the equivalent of highlighting your notes instead of actually solving problems. Highlighting isn't solving problems, and making tree diagrams is not solving problems. Question 7. Find a normal vector for a line that is parallel to. Okay, so I'm going to draw the input line. That's, let's give this a name. I'll call this Charlie, or line 1. Okay, and it has a normal vector and a direction vector. So there's its N, normal vector, and there's its V. And we want a new line that is parallel to this line. So there's our normal vector M, and here's our direction vector U. And we want M, which we can get. I'm going to highlight the special bird. Parallel. That was why the new line's pointing in the same direction now. We can get M from N. They're pointing the same way. M and N are collinear. So the normal vector for the new line is M equals 3, 8. So we didn't need V. Whew. Almost posted a video with incorrect answers. Okay, question 8. Find a normal vector for the plane that contains the lines given. So it's kind of silly to draw a picture in 3D, 2D projection of a 3D image. I'll do my best. There's a plane. It's infinitely thin. I'm going to draw 2 lines on the plane. There's the first line, line 1, and then there's a second line, line 2. It doesn't really matter if they cross or not, or does it? Yes, it should. It should cross. Make them cross. L2. So those are the 2 lines that are sitting in the plane. And what we're asked for is the direction vector. We want this. The normal vector, I mean. And the way we get N is we take the cross product of the two direction vectors for the lines. When you do a cross product between two direction vectors, so 1, 2, 3 crossed 2, negative 1, 2, what you get is a new vector that is simultaneously orthogonal to both of the input vectors. Now the first input vector, 1, 2, 3, that's a line that is, that's a vector that is in the direction of line 2 and in the plane, like pointed in the same direction as a direction of the plane. And then the same with 2, negative 1, 2. That's also something that's in the plane. And if you cross them, you get something 90 degrees to it, to both inputs, which means it'll be 90 degrees to the plane, which means you can use it as a normal vector. There's really two common answers that will come out of a question like this, either 1, 2, 3 crossed with 2, negative 1, 2, or the reverse, crossing the other order, which will give you the negative of the first way. Anyway, so here's again how we did cross products in class. If you have your different way, if you sing the 1, 2, 2, 1 song, you can continue to do that. Make 2 copies of the first vector in the cross product, and make 2 copies of the second underneath. Cross out first and last elements, first and last columns, now that we're using that language. Make a bracketed term to contain the answer with minuses in between, and then we have down components minus up components. So the first down component, 2 times 2, 4, second down component, 3 times 2, 6, third down component, 1 times negative 1, negative 1. Now we have minus the up components. Negative 1 times 3, negative 3, 2 times 1, 2, and 2 times 2, 4. And then simplify. 4 minus minus 3, 7. 6 minus 2, 4, minus 1 minus 4, minus 5. And that's going to be a normal vector n that's at 90 degrees to the plane. You can always check these by doing a dot product n dot both of the input direction vectors. So let's try it with 1, 2, 3. 7 times 1, 14, plus, 7 times 1, 7, what am I doing? 7 times 1, 7, plus 4 times 2, 8. So 7 plus 8, 15. Now we have the last part, negative 5 times 3, negative 15. So negative 15 plus 15, 0. That works. And the same thing for the second vector. 7 times 2, 14, plus negative 1 times 4, so that's 10. And then plus 2 times negative 5, negative 10, so 0. So both dot products are 0, which means that this is at 90 degrees to both of them, which means this is a normal vector for the plane. Okay, and then question 9. Again, here we're asked to find a vector for an object. This time we're asked to find the normal vector for a plane, and this is fast. We can just quote what the result is. It's a coefficients in front of x, y, and z. This is in point normal form for a plane. Point normal plane. So n is 3, negative 4, 2. That's it. And the last one, question 10, we're asked to find a normal vector for the plane that has the equation x is equal to 7. I'm going to rewrite that. I don't like that. That's 1 times x plus 0 times y plus 0 times z. It has to have a third component because it's a plane. If it was 2 components, it would be a line. That means the normal vector n is 1, 0, 0. Looks strange, but that's the answer. Alright, and that's it.